Let's start today's class. Oh, let me share the screen. Okay. I think my screen is visible. Okay. Then let's start. So let's first revisit what we have learned so far. So we have learned what is the dynamics of any initial condition under a linear map or a affine map. So whether any initial condition will approach towards a fixed point or not, that we have learned so far, and that we know that only for a linear map or affine map. So the special things about these two types of map is that function is linearly proportional, or it's the x is the linear x present there linearly. And for that map, for those kinds of map, we have found that from the tangent, from the slope of that linear map, we can we there is we prove that theorem that we can conclusively say that if its slope the slope is less than 1, then any initial condition will asymptotically go towards the fixed point, and if the magnitude of the slope uh, becomes greater than 1, and we have seen that any initial condition will go further away from the fixed point. And in this context we have seen that we can map a physical thing, which is that how mammals regulate their body temperature through uh, means how can we map the mammal's body temperature through affine map. Now we can do same map, but I will not do the step that we have done previously. I will only write the equations. So I have said you that I will show you how to map. So let me first do that, how to map hormone regulation in endocrine system. Hormone regulation regulation in endocrine system. Endocrine system. Okay. Now consider the regulation of a specific hormone. Suppose that cortisol, that depends on the two factors. So suppose the if we want to measure the density of the hormone at a particular time, so it should depend on the hormone density at the previous instant. Suppose I want to check hormone density at n plus 1th minute, it should depend on the hormone density at the previous instant, means previous instant previously how it was, and what is the base rate of the secretion of the hormone. And a is called feedback coefficient, which will says that how efficiently our body is managing the density of that hormone. So a basically says that the a actually characterize that how our body is regulating that hormone density. Now you see that we can write a equation of the, if h is the density of the hormone, so we can write these type of equations, means we can model the hormone regulation in endocrine system in this way. And as we have seen in the previous case, we actually we have seen for the body temperature regulation that if A is, and this is a affine map, so this is again affine map, affine map, and we know that for any affine map, as we have seen in the previous class, that if the magnitude of the A is less than 1, then we will see that the hormone density will attain a fixed amount, means with time it will approaching towards the fixed point, and in physical terms it means the hormone density will become fixed in our body. And if A is greater than 1, we say that the body cannot regulate that hormone, and it may that that particular hormone will reduced or decreased depending upon A or B. So if A greater than 1, that I will say that body are not, our body is not able to maintain a fixed amount of hormone density in our body. So that's thing, and I think you can do by it yourself, that how means by drawing a power diagram you can clearly see, you can at when A less than 1, that it is attaining that fixed point, a stable point, and if A greater than 1, it will diverging from A greater than 1. If it will become lesser, it will continue to be lesser further, and it will go away from further from that fixed point. So it's like that. So it is a fixed point. So if you if A greater than 1, then you see that if you start from an initial condition lesser than this point, it will continue to go in this direction, and it will go further away from this point. And if you start from here, you will see that it will go further away from that. So that is basically thing. Now there is no new thing to learn. So let's move into the next thing. So is it clear, Subhusaji? Or if you have any question regarding this? Huh. 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 Okay. Then let's move toward the next thing, that is called the. So so far what we have done, so we knew that any function, any map whose dependence of the function x is linear, that means if it is x plus b, so b could be 0. If b is 0, then it is linear, or if b is not equal to 0, then it is affine. So we know that how to say about the behavior of that function, a map, any initial condition under this map, if it is linear. But unfortunately for us, means it is why not fortunate, because I will say that in later case you will see that it is the basically thing. So all the map that will actually approximate or model the real world system, that should be necessarily non-linear, that can't be linear in nature. So most of the map or if you want to most of the map which models real world problem, most of the maps which model the real world problems, those maps are non-linear in nature. Non-linear in nature. And in the later on in this course, we will see that this because of this non-linear property, the most of the interesting things of the dynamics will appear, such as cycle limits, such as cycles, such as orbits, close orbits, close periodic orbit, chaos or so things. But for now, we do not know how to analyze the dynamics of a nonlinear map. And if I want to see that whether means, whether any, if I start from an initial condition, it will eventually hit the fixed point, or it will go further away from fixed point. So there is no way to analyze that things in terms of if I say that in terms of non-linear map. But we know that for the linear map it is very easy. So we have seen that for the linear map, means for the affine map and linear map, it is very easy to check whether or not that any initial condition will hit towards the fixed one or not. If the slope of that, depending on the slope, if the slope is lesser than 1 or greater than 1, we can easily say in general whether what is the fate of the system. Now in this class I will try to use the fact that we have learned that can we will want to by anyhow, means the question is, can we approximate a non-linear map? Can we approximate approximate the non-linear map by a linear map? This is our question. So we will see that yes, we can, that by we can approximate a linear map to analyze this non-linear map. So we will see that first thing. And if I can write any linear map which will be very closely mimicking the behavior of the non-linear map, then from that linear map, since we have developed already our tools from which we can say that if what is the behavior of the system if the system evolves according to the linear map. And since we can approximate the non-linear map through a linear map, and so we can say then that non-linear maps dynamics will be closely approximated to the dynamics of the linear map. So that is basically we want to see in this class. So let's see. So first of all, is there anything? So to check that, first thing, check that is there is any linear map which closely mimicking that behavior. So first let us draw any non-linear map. Suppose this is x, this is f of x. Now let's draw some non-linear map. Suppose this is a non-linear map. Now if you connect, suppose these 2 points, so A or B, let's connect these 2 points. Connect means by drawing a straight line. It's not looking quite straight line. Okay. Let's draw like this. So you see, suppose you draw A or B point, but you see that this line, this red straight line, this linear line actually is not approximation of this blue curve. But interesting thing happens when I tries to decrease the distance between AB. So suppose now if I draw this, so previously it was like that. Now it will be like this. So you see, as I decrease, so suppose that B1, suppose this B2, as I decrease the distance between A and B, the straight line between A and B2 will closely look like the map. So if I decrease further, you will see that is more close or more closely mimicking the non-linear map. So if I use, instead of use B2 if instead of point B3, which is more close to A. The straight line between A and B3 will be more closely behaving like that nonlinear map. So A and B, the straight line, that is linear map, AB3 linear map, closely mimicking the behavior of the nonlinear map Fx. So from this we have an means that we have an idea that if I small and if I just decrease the distance between A and B3, and at the point if its distance is nearly 0, so it will be exact to this, the behavior will be exact, the behavior of the straight line and the behavior of this nonlinear map will be exact. But there is a catch, so that point will be a single point because the distance is A and B3. If it becomes 0, then means that A and B3 is the same point, and that curve is called the tangent of that, or it is called the tangent of this curve at point A. So that will be, we know if the distance AB3, the distance is, if it is goes towards 0, that means point A and point B3 will be same. So that's why the distance is actually is closely same. A point A and B3 is same. That's why we say that the distance is 0. And from the mathematics we know that if I draw a line which only touches a point is called the tangent of that curve. So from here we know that in point A, that system exactly behave like that tangent, that non-linear. So the tangent means that non-linear system, non-linear map behaves exactly same as the linear map tangent in the point A. So that we know. Now the question is, can this tangent not only since we know that this is exact behavior, now can we say something about that, whether or not the closely neighboring point also closely mimicking the behavior or not? So let's see that. First of all, we will see it by zooming out that region. By zooming out the region, we can see that actually in the close neighboring points also fall to the line. So I will see that. So first of all, let's see. Let us write the equation of the tangent. So you see here in this point, and suppose this point is P and this point is X, and this is the, so I have to, if I give you X, what is that? Y. Suppose this is Y, or maybe this is the equation of tangent. So suppose it is the tangent X, and this point I know this is P and F of P. This is the point P comma F of P. Okay, I can draw a line here. So from this and I know the tangent at this point. Suppose the tangent is F prime P. So we have learned that how to calculate tangent. Tangent is the first derivative. So we know the tangent F prime at P is equal to, so it's this, how this is P minus, so this is tau X minus P by, this is X minus P, so x minus p. So you can write that tau x is p plus x minus p into f prime p. This is the equation of the tangent. Why you are interested in the equation of the tangent? Because you see, if I put x equal to p, what it will become? X at x equal to p. Oh, sorry, this is, I think, f p. This is f of p. This is f of p. This is f of p. So x equal to p, you will see that tau p is actually f of p. So that means that tangent actually similar, same as the map, and the first derivative of this at the point p will be same as at point p will be same as f dash p. So from these two you can say that at point b this tangent is same as the function. So that is our motivation to to see is there exist any linear map which will be exactly or closely mimicking the behavior of that map. And indeed it is true that this tangent can be a good thing to go with. So is it clear, Subhusaji? Okay. Okay. Now next thing is to check. Next thing is, so far so good. We have learned that there is a linear map which can do what we want. Now next question is, can we approximate the neighborhood point by this map or not? So to see that, we have to check a thing is called zooming out. So if I zoom nearer to this point, suppose if I zoom nearer to this point, can we say that the neighbor point of this can be closely matching with that point or not? So let's see. Zooming out. Zooming. So Bhudaji, I have to take a call. So spare me 5 minutes, and I will come to this. Just give me 5 minutes, and I will continue these lectures. Okay? Is it fine? So I have to take a call. So that's okay. That's very important for me. Thank you, Subhusaji. Uh, so let's start. So there is a tangents via zooming. So uh, we want to see whether or not the nearby points are can be approximated by the tangent or not. So to see that, we have to first see a lemma which is looks like this. So if I approach towards the point, so suppose if I approaching towards the point xp, the distance between the x and p, it doesn't matter whether I am coming from suppose I am coming from this side or this side. So the distance between my a point x and p into that the fx minus tau p at x. So at point p I am drawing a tangent, it will be equal to 0. So this is called something very strong thing, which is like that the f of x and tp of x means the tangent when the x close to the p, these two are actually very close. It's not at the point is exactly same, but also near in the nearby region it also very fx and the tau px are very similar. It's not very similar, it is like that. This is a very small quantity, you see this is very large quantity, this is a large quantity, because if x and x minus p is, if x tends to p, that means x and p is very neighborhood point, then the distance between that two will be very small. Suppose this is 0.0000001 1 2 3 4 5. So this is x minus p. Suppose x minus p is modulus is this, that means a 1 by x minus p is 1 by 0.1234 1. So this is will be 10 to the power 5. So you see limit x tends to p, then 10 to the power 5 times fx minus tau px will tends to 0. Now you see if fx and tau p only, suppose that fx minus tau p is only 0.01, then you see it if I multiply this, suppose that suppose fx minus tpx is 0.01, if I see that this is that these two are that close, then if I multiply by 10 to the power 5 into this fx into tau px, you see 10 to the power 5 into 0.01, that will be 10 cube, that is 1000. So it is not at all close to 0. So that means it is not like 0.01 differ, it differ very, means differ, it's means the fx and tau x is very close, it should not be 0.01, it is like that 10 to, means like that 10 to the power minus, means it is very close, it remain very close after multiplying a large number. So this large number, this the multiplying by the large number, it's called zooming out. So if I show you geometrically, if I show you geometrically, if I show you geometrically, so this is like, so suppose this is a tangent, suppose this is a tangent, this is a tangent suppose, and this region is suppose this is a p. Now this is suppose x minus p by x minus suppose this is x minus p by 2 some point here, and here x minus p by 2, then the box, that box drawn by these, suppose box is drawn by these, and you see that this is also x minus p, this is also x minus p. So if I draw a square whose dimension is x minus p cross x minus p, and if I zooming out to means if I take it out and make this x minus p to 1, suppose now I zooming out means if I make it large, so make it large means suppose this is, draw it here. Now if instead of x minus p, if I in this case it is x minus p, and now in the zooming version of this it is become 1, this is 0 to 1 and this is 0 to 1. Now this box means I have zoomed out this portion and we are seeing exactly same thing, so we will see like very close, this is maybe that line and this will be the tangent, this will be the tangent, and you see after zooming out also this remain very close to that original nonlinear map. That is the basically this lemma says, lemma says. And why we are interested? We are interested because by applying this lemma we can say that, so we can say something about, suppose we can say something about the behavior of the system near to the fixed point. So if I can say the behavior near to the fixed point, and by approximating this tangent, that is our actually motivation. So let's see from let's see by using a computer that will be more visible, that will be more appeal to visibly. So first let me use the equation. I will show you that the fx equal to half x into 1 minus x. Okay, now if x equal to half 1 minus x, what is its fixed point? What will be its fixed point? So one fixed point is obviously x equal to 0, because then we know the definition, x should be fixed point. At the fixed point this should be followed, p equal to f of p. Now if I put x equal to 0 here, then means 0 should be f of 0, and you can check that actually that is the case, 0 will remain fixed under the action of this map. So this is the fixed point, x equal to that, x equal to 0, and you will find that this is the only fixed point for this map. Now let me use the computer to show you that near this fixed point we can approximate that map by its tangent. Let me first go to this map. Okay, zooming, suppose first option, let's see in the full version. Now you see here this red dot is the fixed point and this black dotted line is the tangent to this fixed point origin, x equal to 0, and this is the curve half equal to this, the nonlinear curve. Now from here it is not quite obvious that nearer to this fixed point the black dotted line actually shows the behavior of the blue line. So now let's look into the close look close, that means if I zooming out, if I only see this portion, now you see that now it is seem that this black dotted and the blue line are closely matching. Now let's more zoom towards it, so make it suppose 0.25. Then you see when I am zooming out the region, we can find out that this black dotted line and the blue line becomes quite similar. Now let's me zooming out one more time, so suppose zooming in 1.25. Now if I zooming out more, you will see that this blue line and this black dotted line are become quite similar to each other. So that means yes, it is possible that by applying, means from a linear map, from a linear or affine map, we can approximately tell the behavior of a non-linear map. So and that so so it is true basically. So we have found that we can there exist there exist there exist affine map which closely similar which is closely mimics the actual non-linear map, and that affine map is nothing but this the tangent map that we have, the equation of the tangent, that is exactly the tangent. This is exactly the tangent the equation will be, the tangent will be fp plus x minus p into f prime p, tangent at the fixed point. So if I want to know whether the fixed point is attracting its nearby initial condition or it is repelling the nearby initial condition, we can use simply this affine map instead of that non-linear complicated map. We can use only this linear map, and we know from our previous class that since it is affine map and this f prime p is nothing but a, and depending upon this f prime p, we can say whether or not, depending upon this f prime p, whether or not less than or greater than 1. If less than 1, we can say that all the neighborhood initial condition will come towards the fixed point p, and if becomes greater than 1, if it becomes greater than 1, then the all initial condition will go away from the fixed point. So is it clear, Subhadaji? Okay. Okay. Okay, then it's fine. Okay. Yeah. Hmm. Oh. Hmm. Yeah. Yeah, exactly. This is actually concept of the that differential calculus, and it is exactly what you are getting there is correct. So that I am saying. So yes, there is a method Now let's see by some example, then it will be clearer. And in the next class I will show you some real world examples, so that will be more fun to do. So let's first introduce these mathematical concepts. So first, define the attractors and repellers. So from our the previous class we know that if this slope, that a prime p, that at since this is a tangent, so this is the slope at the fixed point. So depending upon that slope is whether less than 1 or greater than 1, we can say about that whether the initial condition will go converge to the fixed point or it will diverge from the fixed point. So let's see. So first case, if f prime p is less than 1, if f prime p is less than 1, suppose this is x axis, this is y axis, and this is the identical line. Identical line means y equal to x, and suppose this is my non-linear map. This is non-linear map. Now you see, at this point, since this is the point where this is fx, these two point cut each other, this is called the fixed point. And if I draw a tangent in the fixed point, you will say it will be like this. This is the tau px, and you see this tau px, the tangent is that f prime p is lesser than 1, and we have drawn it is from in the our previous class that if f prime, if the slope is lesser than 1, it will be always in this region. Now if it is, then let's just draw some cobweb diagram to see. Let's draw some cobweb diagram. So first, suppose here is my initial condition x0. So if I go upwards, it will hit here. So this is my first iterate. So this is actually x1, x0. This is my first iterate, x1. Now to generate the second iterate, I have to create a point which is x1, x1. Now here this is the my first iterate. This is x1. Now this is my x2, x1, sorry, x1, x2. This is x0, x1. Now here too will go in this direction. Now you can see that it is closely approaching towards the fixed point. So it is closely approaching towards the fixed point. So from here to it goes here, then from here to here, then here. So it is continuing and this goes towards the fixed point. So it is the case if f prime p is less than 1, then it is going to 1. So another case, let me show this case. It is f prime p, actually f prime p lesser than 1. Now let's show the f prime p is greater than -1. So that will look like, this is y, this is x. So this is my identical line. This is the identical line here, and so this is the identical line here also. This is y equal to -x. This is y equal to -x. Then if it is the fix, so the tangent should be like this. So maybe a curve like okay, this is exactly become this, so it will not help. So something like that. Maybe maybe it's not, I'm very so let's draw this instead. So here not very much artistic is required to draw this line, so let's draw this line instead. So this is y equal to x this line, and suppose this is another map. If I and suppose this is the fixed point, and if I draw the tangent here, the tangent will be higher than 1, so the tangent will look like, suppose in this point the tangent will look like, this will be something like this. This is the tangent at this point. This is the tangent. This is the tangent at this point. Suppose I am pretty bad at drawing. This is the thing, and now this is the tangent at this point. This is the tangent. Now basically this tangent, this, and you can see from here the tangent slope is higher than 1. Now for this curve, let us draw a cobweb diagram. So let's start from here, and it is the fixed point. Now if I start from here, x0, so this is the point x0 comma x0. Now if I go upwards, I'll hit this point. So this is the x0 comma x1. So here somewhere, so this will be my first iterate x1, and if I now continues, and you can see from here to here it goes, and here to here. Now you see that from the initial condition actually goes further away from the fixed point if f prime p is greater than 1. So that's also from here, by using cobweb diagram also we can see that if f prime p is less than 1, then the initial condition come towards this fixed point, and if f prime p is greater than 1, the initial condition go away from this fixed point. Because of that, in mathematics it is called that if at fixed point p, fixed point p, if the slope f prime p, or the derivative, first derivative at p, so dfx dx at x equal to p, if f prime p is the modulus, the magnitude of the f prime p is less than 1, it is called the attractor. Because you see here all the initial conditions near about this point, it will attract all the initial conditions, so that's why it is called attractor. And on the opposite, if f prime p is greater than 1, because you see from if f prime p is greater than 1, all the initial condition will go away from this fixed point, so that's why it is called the repeller. Then the fixed point, here this fixed point will be called attractor because the fixed point is attracting all the initial condition, and here in this case if f prime p become greater than 1, it is called the repeller because the fixed point actually repelling all the initial condition. That's why it is called the repelling fixed point, or there is a repeller. So that's all. Now let's go towards the theorem that I want to say here. So that is the main thing here. So the theorem is saying that it is from the cobweb diagram we can see for only one initial condition. Now if I want to say in general whether or not true that if f prime p is less than 1, then we can say that this fixed point is a attractor, because you see only for a one initial condition. Now to check whether, anyone can say that I can have a point here, suppose x0, which will not be attracted by this point. Then to check that point, I have to again draw a cobweb diagram and to show that individual that no, that x0, for x0 also it goes towards the initial condition. Now anyone can ask any initial condition and to in this way you have to check infinite initial condition to say anything conclusive about that nature of that fixed point. So that's why the theory comes. If I can theoretically say, or if there is any theorem, then we don't have to check all the initial condition. By the theorem we can say that all the initial condition in some region will actually go towards this fixed point. So let's prove that. That's not is mathematically proved. So this is main theorem is. So theorem is basically nothing. Theorem is says that if P is the fixed point of F, then fixed point F, then and another if F prime P is its magnitude is lesser than 1, then it says there exists a neighborhood. It is called open neighborhood. So it is basically mathematics is open neighborhood. So this means suppose you have a fixed point here. Suppose you have a fixed point here. So you will have a open interval I and open neighborhood, and any initial condition if in between this open interval, in between any open interval, any initial condition, so any initial condition either means any individual conditions asymptotically reach to the fixed point. So it says that any fixed point if you take here, any fixed point in the, so theorem basically says there exists if F prime P become lesser than 1, so there exists an interval. It doesn't say about that how long that interval is or how big that interval is, but it says you will always find a non-zero open interval, and there the initial, if you take any point in that in that open interval as an initial condition, and if you iterate through the map F, it will ultimately reach to that point. And the reverse is that if F prime P is greater than 1, then it says that there will means greater than that there exists an open interval. You will say there exists an open interval for which if you start from this initial condition, you will see that the distance between fixed point and the iterate, suppose x k, suppose kth iterate minus suppose this fixed point is P, will be always the kth plus 1, the next iterate point will be always the distance of the next iterate will always higher than the previous iterate. So that is the thing. Did you means is it clear, Subhaj? So this is the theorem. Now we will prove that mathematically. So it's a little bit okay. Now let's see. So to prove this mathematically, so we have to prove first one lemma, which is one lemma is f of x minus f of p is less than a x modulus. Let's see modulus x minus p, where a is less than 1. So it says okay, so lemma is like that. So if f of p is modulus of f prime p is less than 1, then there exists an interval. So there exists an interval, and suppose there exists an interval I, open interval obviously, there is exist open interval like this, and all the points, all the x which belongs to the open interval. So if you take any point from this open interval, they will if this is the x any point from this interval, then this relation will hold. That means fx minus fp should be lesser than some constant a, and this constant obviously less than 1 into x minus p, the distance between. So this, suppose this is some open interval, suppose this is the point p and this is the open interval, and you take some point here, so here x and p, so the distance between the x and p is x minus p. If your f prime p is less than 1, then you will find there exists an interval, open interval, and all point, if you take any point, that means all point from this interval will hold this equation, or this is the lemma. So let us prove that. It is the proof is very simple, but let us see that. So since we know from the definition of the definition of the derivative, so this is definition of the derivative, we know that f of x minus f of p by x minus p is nothing but the first derivative at f prime p. So this is the from definition. Now see, since we know that f prime p, modulus of f prime p is less than 1, so that we know. So we can say there exists a constant, suppose a, which also follows this relation, because less than a, less than 1, because you see that a is less than 1, so we can choose some a which follows this relation, so we can see that. Now another thing is, we have to prove that there exists a interval I, and that is we can prove from a theorem of the limit. So this is suppose open interval p, and this is suppose the function value, suppose this is f prime p here. Now we know that f prime p has to be, so f prime p is less than 1 means f prime p should be greater than minus 1 and less than a. So that means somewhere, suppose that this is minus a, this is plus a. So f prime p is somewhere in between minus a to plus a. Now from limit, as you know, so a little bit of differential calculus. So you know the limit means, if I approach this point from right hand side or left hand side, it doesn't matter. So it is called like limit x tends to p plus, suppose, so from this side I am approaching p, it doesn't matter, or I am approaching x tends to p minus from this side, these two should be equal, then I will say that the limit exists. Since the limit exists, we can say that if you come from this side or this side, in the neighborhood of these two will be very same as a prime p. That means you have a closed interval where your limit exists, and the existent limit should be close to f prime p, because if it is not close to f prime p, then at the point it will not become f prime p. So it has to be close to f prime p. So that is actually says there exists a limit. So is it clear, Subhuji? Because I know it is a little bit mathematical thing, but is it means intuitively clear that why there will exist open interval from the definition of the limit? Huh. 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 Yeah. Huh. So you see that to exist the limit, you have to have this condition, that means it doesn't matter in which direction you are coming towards this point. Suppose you are coming from this direction. Suppose this point is p plus epsilon here, sitting here, and suppose here p minus epsilon is sitting here. So you are coming from this, so you are saying that, so a prime p plus epsilon. Now limit says that, let me do it in this way, then you will limit that, okay, this is p, so limit x tend to p plus epsilon. Epsilon is very small, suppose that p plus epsilon f of x minus f of p, p, okay, this is x minus p. Okay, if you are coming from this side, now this side means if you epsilon and epsilon tends to 0, epsilon tends to 0. Limit says that these should be equal to limit x tends to p minus epsilon and epsilon tends to 0, and same thing. So you are not coming from this side, you are coming from this side. Now suppose you reach here, and from here you reach here. The limit says to exist this limit, these two should be very close to each other. So this and this and these three should be very close to each other, and we will say that limit exists if when these two reaches very close to neighborhood, these three will be equal. So in limit terms it is called limit, this term is called x tends to p plus, you are coming to the point from the right hand side, or equal to means in the above to, and if you go reach to the point p from the below, it doesn't matter, it should be equal, and these should be equal to the limit value, then we will say the limit exists. So this means this should be continuously this means these values, that the value of f prime p at the neighborhood of point p from the above side and the lower side should be closely means close to the f prime p. If it is close to f prime p, then since f prime p remains in between plus a to minus a, then these values should also remain in between plus a to minus a, because these are very close to f prime p. Is it clear? So that means you will find a limit, you will find an interval where that the f prime other means that the f prime x should be remain very close to f prime p. Okay. Okay, I know that it is means it's quite uneasy to grasp these things. Means okay. Then you will find it's so that's it. Now if it exists, this means it proves that minus a means, suppose since fx minus f of p minus x minus p less than. So this says that if I come from this point, so this factor f of x minus f of p by xp remain close to fx, f prime p, and a, since f prime p belongs to plus a minus a, then this quantity should also belong to minus a to plus a, and this is belong to minus a to also. Okay, this is not. So this means f of x minus f of p by x minus p, its modulus should be less than or equal to a, or f of x minus f of p, its magnitude should be less than equal to x minus p. So now you see that there exists a open interval where this relation holds. So we find that there exists an open interval where this relation holds. Now from here to prove that the theorem that prove that if I take any initial condition, suppose this p is a fixed point. Now if I take any initial condition, it will convert to the fixed point. That is not very difficult. So let us see that. So suppose p is the fixed point. If p is the fixed point, then we know that fp equal to p. That means f of x minus p should be less than equal to x minus p. Now suppose this is the kth iterate, xk is the kth iterate of the theorem, then that means and f of xk minus p is lesser than equal to a xk minus p. Now this is xk means xk plus 1 minus p lesser than a xk minus p. Now if I and it is only valid inside this open interval. If I take any point x0, suppose, from that interval, then its relation will hold. So this from this relation will get that x1 minus p should be less than equal to a x0 minus p. Now in the second iterate, what it will be? x2 minus p will be lesser than a x1 minus p, and since we know that x1 minus p is less than a minus x0 minus p, so if I put here a, it should also less than, so it will be a square into x0 minus p. Now you continue in this way, so xn minus p would be less than equal to an x0 minus p. Now since a is less than 1, since we know that a is less than 1, from here you see a is less than 1, f prime p, from f prime p a came, and a is less, since a prime p is less than 1, a should be less than 1, and we know that limit n tends to infinity, a to the power n tends to 0 if a less than 1. So then it says that limit x, now it will be says that limit n tends to, now if I sim as we have done previously, if I do this, then I will say that limit n tends to infinity, a n x0 minus p will also approach to 0. Now since you see this means this will means limit n tends to infinity, since this is 0, this side is 0, so that means xn minus p should be lesser than 0, p modulus less than equal to 0. Since this is the, okay, let me write it in this way, this is the right hand side of this equation. So in this left hand side, suppose it's, if I go here and limit n tends to infinity, limit n tends to infinity, and you see that this quantity becomes 0, so limit n tends to infinity, xn minus p should be less than equal to 0. Now you see this is the magnitude value, so this is only positive, so this cannot be less than 0, it actually equal to 0. Limit n tends to infinity, so this we know by definition this cannot be less than 0, so it should be equal to 0, so xn minus p equal to 0, so So this becomes xn limit n tends to infinity xn equal to p. So from here you see that if I iterate infinite times any initial condition x0 which belongs to this open interval. If I take any initial condition from this open interval and if I iterate it infinite time, it will eventually go to that fixed points. So that proves that f prime p, if f prime p become lesser than 1, then we can say that this fixed point is a attractor. This attracts all the initial condition which remain inside this open interval. So that's all. Is it clear, Subhutaji? So okay, if it is clear, then we will end this meeting here. In the next class we will see something, means if I show you some example from nonlinear map, that will be very good. So then let's meet in the next class. Okay. Ha. Now I will give some real world example. Okay. Thank you for joining. Then I am closing this lecture.